So for section 1.5, we also are going to cover vertical asymptotes. Now, the line x equals some value. So this would be where you have some kind of vertical line, maybe at x equals 2, something like that. The line x equals a, so it could be anywhere in your graph. It's a vertical asymptote of the graph if, when you investigate the limits, the limit as x approaches that value from the negative side of a function is plus or minus infinity. Or you might have it from the other side. The limit as x approaches a from the positive side of that function is plus or minus infinity. So again, I'll kind of go over that. If you're looking at a limit as you approach a certain given x value, if the limit is infinity, like as you get closer and closer to that x value, it goes up and up and up, or down, down, down. If the answer to the limit is positive or negative infinity, that means you've got a vertical asymptote here. Same thing from the other side. If the limit approaches negative infinity or positive infinity, that means there is a vertical asymptote there. Okay, so we have kind of been gearing up towards this, and we've already been investigating this, but we're going to start with looking at finding vertical asymptotes. So first, when you're looking for a vertical asymptote, you first will start with discontinuities, and that was everything we learned on Friday and practiced on Monday in school, or other days if you're listening to this another year. But how do you find a discontinuity? In the section right before this, we learned how to do this. And what we did is we set the denominator equal to 0 and solve for x. When you set the denominator equal to 0 and solve for x, whatever x equals, those will be your discontinuities of any kind. Now, if you have a removable discontinuity, that means there's a hole there. Talked about that, in the last section. If you have a removable discontinuity, which means when you go ahead and simplify, it cancels out, it's removed, that means that discontinuity, there's a hole in the graph. If it's a non-removable discontinuity, that means in the graph there's a vertical asymptote there. So we will look at 3 examples, and I'm sorry about my formatting. It ended up printing kind of odd. All right, so first, find the vertical asymptotes, if any. So when you're looking for a vertical asymptote, the first thing we need is all of the discontinuities, and then the second thing is we will simplify, and any that are left are vertical asymptotes. They're non-removable. So there is no fraction here. There's no discontinuities, so there are no vertical asymptotes in the first one. I just wanted to remind you that there isn't always a vertical asymptote. It takes a certain kind of function with a fraction. Next, the discontinuities here are at x equals 1. And then as we simplify that, we can't simplify it. So that means this is a non-removable discontinuity, which means x equals 1, there is a VA or a vertical asymptote at x equals 1 because it was a non-removable discontinuity there. Now this one, again, it printed weird, and I don't know if it printed like that on yours, but it did on mine. So I am going to simplify this. Looks like I can factor the bottom. Okay, so there are 2 discontinuities. Looks like there's one at 1 and 4. All right, if I go and simplify, I can remove and cross out 4. That means 4 is removable. A removable discontinuity is a hole. So we know for this graph, there's a hole at 4. This example asks for the vertical asymptotes. So the non-removable is this one that's left over, the 1. And so that means there is a vertical asymptote there. So we know there's a vertical asymptote at x equals 1.